Okay, for this lecture, there are no drawings for you to have to do. It's just kind of some guided notes and questions. They are in order as the lecture goes on, so you can kind of just, as you're watching, answer the questions as we go. But we're going to talk about property lines and just kind of the general site. We're not going to do any practices with it because we'll do that when we get into the CAD stuff, as well as just foundations and footings and some of the utilities that you can find on a site. Let's put that in full screen. And now we're going to get out of full screen in a moment. So the boundary lines of the building site are shown in what we call the site plan, and the direction of the property line is usually expressed as a bearing angle. So the bearing of a line is the angle between the line and north or south. Bearing angles are measured from north to south depending on which keeps the bearing under 90 degrees. Angles are typically expressed in degrees, minutes, and seconds. So there's 360 degrees to complete a circle, 60 minutes to a degree, and 60 seconds to or 60 minutes to a degree, and 60 seconds to a minute. The point of beginning, or the POB, may or may not be shown on the site plan. If the point of beginning is not shown on a site plan, so in this one it is shown, but if it's not, you pick a convenient corner. Corners are usually marked with what are called IPs, or iron pins, or some permanent feature. And so I have linked here is actually just a little scan I took of this is absolutely not the official site plan for where I live, but this is my landlord's dad made this picture years and years and years ago. And so with all of the IPs, like this is just a stake and a chestnut. This is a stake in the Fresnel line. There's some of them that I don't know if they got picked up, but I always found them kind of nice because it was just like, yeah, there's a white birch here. That's one of the stake parts. I would probably pick more permanent features than, like trees or whatever. But this is still a site plan for the property boundary lines of like the property where I live. And I thought it was kind of neat. And you can find these boundaries with like just a handheld compass, really. The approximation of your iron pins and the property lines that you put should be accurate enough to help you find those markers in real life at the next corner. So all of your construction activity should be kept within the property boundary lines unless you have permission obtained from those neighboring landowners. So when you are clearing the site, you're really then entering the first step of actual construction, is just to prepare it. So clearing any brush or trees that are not to be part of the finished landscape. The architect may choose what trees to remain, and it's based on a couple of factors. So trees and other natural features can be a very important part of architecture. Not only just are they just kind of, in my opinion, they bring to that natural beauty of the land, but they can really play a key part in energy conservation. So for example, deciduous trees that have leaves on them, they lose their leaves in the winter, and they can be used effectively to control solar energy hitting a house during warmer months, as we see here, and then so on the south side, that sun, when it's lower in the sky, will go into there and it'll help heat the building. And in the summer, when the leaves are there and the sun's higher up, they'll help shade the house. So this is kind of known as a passive solar feature. In the house that I rent out, they did a pretty good job with that. So the trees then in the trees kind of help shade me in the summer, and in the winter I get a lot of natural light. And then I also have a concrete floor too, which helps absorb all that heat. And then at night, when the sun isn't hitting it, the heat dissipates out of it. It's just a really nice way to try to save a little bit of energy. Any trees that are to be kept on the property or to remain there would be shown as a symbol, typically indicating what like their trunk or the butt of them would be. Areas that are densely wooded to show individual trees, so if it's like a big wooded area, you just kind of would have that squiggly line to represent that it's a wooded edge. And so here, and I'm going to have to just click on that print icon so that way I can rotate it. But this is a site plan for the old Watauga High School. So Watauga High School isn't here anymore. It's now an ASU parking lot. But we can see all the way across the edges, it was just wooded area all the way around here. And I really love these Watauga High School plans. I try to use them a lot for teaching because this is all done by hand. Like, so beautiful, perfect lettering, all done with hand drawings, kind of cool. But so this is just all wooded area in that plan. So once you have your site cleared and you've established which trees or features are to remain, then you would start on the process of grading. So grading refers to moving the earth away from high areas and into low areas, and it's necessary to ensure that water drains away from the building properly and does not puddle or run into the building. In some cases, grading may also be necessary to just access the site in general. So for example, if the site has a steep grade, it may be necessary to provide a gradual slope for your driveway. Your grade is measured in vertical feet from above sea level or a fixed object such as like a manhole cover. And that vertical distance we call the elevation. What can be confusing for some people is we're referring to those heights as elevations, and then people tend to get them confused with the drawing type elevation. We also don't want to confuse it with what we call spot elevations. So spot elevations are used for specific points and the heights there. So in our elevation views and in our section views, we have our spot elevations. Here would be spot elevations in a plan. So it's just saying, okay, at this very particular point, it is 52.2 feet. At this particular point, it's 51.49. And so on. So here again is just another plan from the old Watauga High School, but this was when there was an extension. Oops, now I'm gonna have to go around again. So this was for an extension for an extra building for CTE. And we have here our contour lines representing the various height above elevation, but then we also have our grading lines. And so what these are doing is it's essentially shifting how these contour lines work to then help create a slope going in towards this sedimentary trap here for the agriculture building that was being added on. And so grading then is shown to kind of help show what the newly formed land is going to be looking like. So the grade of the site is shown as topographic contour lines like we just saw in that previous example. These lines are shown following a particular elevation point, and the vertical difference between the contour lines is known as the vertical contour interval. So for plot plans and site plans, it's usually about 1 or 2 feet. So again, or what do I have linked here? No, I want to look at this one again. Sorry. So we have each of these labeled. Because this is such a large site, we're going at intervals of 10 feet. If we look at this drawing here, and I zoom in on the site plan. So each of these dashed lines or hidden lines are done at an interval of 2 feet. When the land is sloping really steeply, the contour lines are going to be very close together. And when the slope is gradual, those contour lines get a little bit more spaced out. So we can see here, we've got a little bit more of a steep slope happening, versus over here, it's a much more gradual slope down. Now, as the builder, you must be concerned with not only of the grade or the contour of the existing site, but also that of the finished site. So to show both of those contours of how it's going to get graded, you have 2 sets of contour lines in your plot plan or your site plan. So the broken lines, the hidden lines, are representing the natural grade of the plan, and these solid lines are indicating the finished grade of the plan. So this is how this contour here is actually going to get moved around and shift around to create kind of a more flat area for the building to be put on, but then also so water, as it's falling down this slope, is going to be pushed away from the building rather than allowing it to kind of just sit and puddle up on the building. So when the natural grade of the elevation is higher than the finished grade, earth has to be removed, which we refer to as a cut. And when the natural grade is at a lower elevation than the finished grade, we have to fill it. And the amount that you would fill it is just the difference between the natural grade and the finished grade. So, locating your building, the first thing you need to do is figure out the position of the building, because we're going to see that on the site plan. You'll have dimensions that show the distance from the street or other significant feature. So I'm pretty sure a lot of these are just, no, this is a different link. Okay. A lot of them are linked to that lake house one. But we have here, and let me zoom over. We've got our site plan here for this 2 apartment kind of complex, and we can see how far away from the property lines is the building. So we can see it's 10 feet from this property line, it's 10 feet from this one, 10 from this one. We have all of those dimensions from the site boundaries to the building. And the other thing that you'll see in your drawings for your site plans are what we call setbacks. So the setback then is the area of the property you are allowed to build on. So just because this property is this phantom line, this heavy phantom line going all the way around, those are our property boundaries. However, we're only allowed to build within this setback area. So on this side, we have to be 15 feet away from the property line. On this side, we have to be, it looks like 10 feet away. On this side, 10 feet away. And in this particular instance, there's a wetland area here that also no building is permitted in. So even though all of this property is part of what you've purchased, you only are allowed to build in this area. And so the setbacks are going to be different based on different local codes or maybe different features. If there's a river running through the property, you can't build within a certain amount of feet of that. If it was construction in a more kind of like urban area, then the setbacks would be reduced because space is limited there and you need to kind of build in whatever amount you can. In areas in Watauga County, it depends on which kind of area, just because it does kind of move from rural and suburban in this county. So some towns might have more steep setbacks than other ones, just to also kind of help with privacy matters. And so we can see on our site plan here, in this particular instance, there really is no setback for this lake house here. Really, there, in my opinion, there should be from the lake, but I can't see any setback on the drawing. So I suppose we could build directly up to the lake if we wanted to. The other thing you may find on a site plan are things like easements, which then have the right to access property. So I don't have any official or any drawings to show you with that. But so there is, like on my property that I live, there is an easement on there for my neighbor to be able to access the driveway that runs through the land that I technically live on, because otherwise poor little Wilma wouldn't be able to get to her house. So there's an easement on there allowing her access to that driveway area. Typically you'll find easements related to utilities. So there might be an easement related to the Public Works Department being able to access like water lines, or for New River or Blue Ridge to be able to access power lines on your property. Now that means that I can't build anywhere on that area that Blue Ridge is allowed to access to do maintenance for their like power lines, because if I built something there, they then have the right to tear it down and get rid of it. It doesn't mean that Blue Ridge is going to have, their company picnic on my front lawn. It just means that they are legally allowed to access this part of my land, so that way they can maintain their stuff. And that's where you'll find a lot of things for easements too. It's just the right to access the property for maintenance work, but really nothing else. And just that if you built something in that area, they have every right to tear it down on you. So once you locate where your property is going to be on your site, then you can start excavating everything. So excavating is just digging to prepare your foundation. The depth of your excavation is measured from a fixed benchmark, and that benchmark can be any stationary object, such as a surveyed point on a street, or a large boulder, or a manhole cover, whatever it may be. All of your elevations are then measured from that benchmark. Only in like a case of like a real coincidence is the benchmark at the same elevation as the surface point of the ground where excavation is to be done. It's really just not going to happen realistically. So the actual depth of excavation is the difference between the elevation at the surface of the ground and the elevation at the bottom of the excavation. At the very bottom of your excavation, which, did I put this on the next slide or not? Oops. Yes, I did, are your footings. Sometimes I forget what I have on each slide. So your footings are placed at the bottom of that excavation to support the entire weight of the building. We place them on unexcavated earth to reduce the chance that soil is going to compact underneath them. This means that the contractor who's doing the excavation must measure the depth of the excavation accurately. Your footings may also be stepped to accommodate any slope within a site, which would require measuring the depth at each step of your foundation. All of the information regarding the footings is found in the foundation plan, as well as the building elevations. And so if we look here, and I'm just going to close out some of these so I don't have too many things open and it doesn't get laggy. We have, so this is our site plan. We have our foundation here. And at some points, this foundation is unexcavated. So in these areas here, as well as here, we don't have any excavated area. We do have stepped footings that are mentioned. And then if we go look at the elevations, which I have linked on another slide, we can then see kind of what those different heights for that stepped footing is. But the footing in the foundation plan are shown as the dashed lines on either side of the foundation wall. So the foundation wall is shown with a thick line, or two thick lines to show the outside and inside, and then dashed along the edges are the footings. The size of the footing may be omitted when the plan is developed for use in several locations. So if this was a building that was just going to be kind of mass produced and put in different areas, then my footing and my foundation is going to vary based on the exact location it's being built on, and especially with those stepped footings. So then that stuff may be not included in a drawing if that's the case. And if it's not put on there, then you'll have to consult with like an engineer to determine how exactly to create your footing and your foundation to keep it within code. So the point of the footing itself is to just accommodate the fact that soil is going to change its shape under force. It's going to get compacted, and with that tremendous weight of a building on soil, it's going to compress under the foundation walls, and it allows the building to settle. So the point of the footing is to try to prevent settling, to spread the weight of the building over more area. The footing distributes that weight so that there is less force per square foot of area. The simplest type of footing that would be used in a residential construction is what we refer to slab on grade, which is despite weather conditions here in Boone, that is what I have at my house. So in this system, the main floor of the building is a single concrete slab reinforced with steel to prevent cracking. And then walls are erected on that slab so that it can support the weight of the building. While it's really more common in warm climates, I do have it in where I live. I guess maybe because it's a small enough structure, it does just fine, but it's kind of the most simplest kind that you would have. So, in your slab foundations, you'll know that it's what you're using because it'll be indicated in a note on the floor plan. If you are excavating for a slab foundation, it's important to tamp or just compact any loose filled dirt, so that way it prevents the soil from compacting under the concrete later, which would cause the concrete to crack or to settle. Oftentimes within a slab foundation, you'll have a thickened slab, which is sometimes called a haunch, to further strengthen the slab where concrete weight, such as a bearing wall, would be located. The haunch is just this extra thick portion of slab that is made by ditching any earth in that area before concrete is placed. Another thing to keep in mind is how far down you have to excavate for your footing depth. So in many areas of the United States, the moisture on the surface of the earth freezes in the winter, and because of this, a frost forms and causes the earth to expand, and the force of this expansion is so great that if the earth under the footing of a building was allowed to freeze, the earth would crack the footing or potentially cause the building to move or shift. To eliminate this problem, the footing is always placed below the depth of any possible freezing, which we know as the frost line. This map here on this slide is only just kind of an approximation of what frost lines would be, where different locations are. So for like accurate information, you'd have to check with local building departments, and they will have specific footing depths required for that area. And it makes pretty obvious sense to me, at least, that, you know, the more north you are, the deeper down your footing has to be, because the colder it is, so that frost line is going to penetrate deeper. versus, you know, if you're in Florida, you're really not going to have the ground freeze too much there. And so like I went to college around like right up here, so we got a pretty deep frost line there right on the Canadian border. The type of footing that we're going to deal with the most in this class and in our drawings is going to be a spread footing, and we also sometimes refer to it as a T-sill foundation because it kind of looks like a T. And in most sections of the country, foundations of the house rest on a separate footing from the concrete floor. And we call it a spread footing because it spreads the force of the foundation over a wider area like most footings do. We can make a spread footing by casting our concrete in a wooden form or metal forms. And in our plan, our footing is shown as those dashed lines going around the foundation walls. And the foundation wall is always centered on top of our footing. So the center line of that foundation wall is always going to be perfectly aligned with the footing itself. The dimensions of your footing is going to be determined by the foundation wall thickness. So a good rule of thumb is that your footing should be twice as wide and at least as deep as your foundation wall. And so it's kind of a rule of, if this is X, this should be 2X, and then how deep it goes down, or its height, should be X as well. That's just a general rule, but it's not like the absolute requirement. You may have to go necessarily a little bit wider or a little bit deeper. So linked here is just a PDF of just kind of the code for how much your footing should be based on how much snow load is going on your roof, what type of building are you creating, what type of foundation is it using, what type of soil is it being built in. All of those factors are going to come into play in how what the size of your footing should be. And that'll all be addressed in the building code. Other things that you may see related to your footings or foundation are related to the type of construction. You'll see this a lot in the section view. So it may be that dowels are used to connect your foundation wall to your footing. It may be that a key is being used to connect the two of them, or it could be that it is monolithic. We're seeing that a lot less now. So typically it's going to be with a dowel or a key, and we'll see a lot of foundations too being built out of. Your footing is cast in place concrete, but your foundation wall itself is made out of CMUs. So not only just the foundation wall itself, or the foundation plan itself, but the foundation plan compiled with the section view helps tell the full story of the foundation. The other thing is, when you're looking at your foundation plan, you want to pay particular attention to any special features, like maybe a fireplace or thickened sections of that foundation wall to help add strength, which we know as pilasters. The footings under those areas will be wider and perhaps even deeper than in just your typical areas of your foundation wall. And there may be times when even like your footing or your foundation wall may be crossed or penetrated by a utility line, and so care has to be taken then when you are penetrating a footing or a foundation wall. If there's not anything shown in the drawings about how that's going to be going through, then prior approval by an engineer must be used, because anytime we're going to be penetrating that foundation wall, we're then risking structural integrity. So we want to make sure that we are keeping our building safe to stand, because, you know, it's just a little important. Column pads are often steel columns or masonry piers, or even on occasion wooden posts used in construction, and there just needs to be a concrete pad or a concrete footing to help hold those columns up. So as with other footings, building codes are used for those areas to consult the design of the pads. These pads, just like your footings, would also need to rest on unexcavated earth. So we see these most commonly for supports for girders in our floor constructions to kind of help our floor joists span over larger areas. Within your footing and your foundation wall as well, you'll typically see steel reinforcements, which are commonly just known as rebars. Rebars are measured based on their diameters in eighths of an inch. And so there's kind of a little chart there that just helps you, I guess, why can't I think of the word? Convert the rebar size number to how big it would be in reality. And so we can see here we have in our footing, we have rebars running horizontally to just kind of help keep it supported. In your foundation wall too, you may have a grid of rebar, or you may just have vertical rebars to help tie it in, to just help keep everything nice and supported. And we use it for reinforcements. And if I had a slab foundation, I'd have a grid of rebar, which I'm pretty sure I have a slide in either the next one or a few ones coming up that shows that. Now, stepped footings are used on sloping sites to change the depth of the footings to help accommodate that slope. And we do that in those steps. When we're using CMUs, or concrete blocks, for the foundation walls, our steps are normally at increments of 8 inches, which allows the concrete block to be laid so that the top of each footing step is even with the masonry courses. Some buildings require several steps in the footing to accommodate steeply sloping sites. So maybe instead of this going up 8, it goes up 16. Depends on exactly what the site is. Stepped footings are shown in the foundation plan by a single line across the footing, which we saw in that other one, and then the different heights of those steps can be seen in the elevations. So, and what do I have linked here? I don't remember linking anything there. Okay, I linked both of these plans there. So here is, for that same lake house that we looked at kind of the site for, here is the foundation plan, and we can see just going across as a single line, we have a stepped footing here, we have a step at the top of the wall, we have a stepped footing, we have a stepped footing, we have a stepped footing. In this garage area, which garages usually almost always have garages have a slab on grade or a slab foundation. We don't ever excavate and have like a basement area underneath it, because the weight of the car is just going to make it collapse. But we still have stepped footing going around it. And so we can see where those steps are in the foundation plan, but the elevations of the house then, I don't know why it always starts me so zoomed out, is where then I can see what those steps are doing and how they're moving, and what the different heights are. And so because this building is being, or the foundation is being made out of poured concrete instead of CMUs, we can still infer, though, that since this is an 8-inch concrete footing, that this right here, this is just an 8-inch or an 8-inch step up. This is a 16-inch step up. And so within our elevation plans is where we then can see kind of how those different steps are happening. Now, your foundation walls. So it depends really what your foundation is being made of, but ultimately laying them out in a plan is going to be the exact same. So when you're using concrete or cast in place concrete or in your walls, and your cast in place concrete has hardened for your footings and the forms are removed, then you can start either having the carpenter create the forms for your concrete footing or your concrete wall, or you can have your mason start laying the blocks for a CMU foundation. And although those materials differ, the drawings, like I said, are interpreted pretty much exactly the same. So you can refer to the dimensions in the foundation plan to lay out your foundation walls, and the process is still very similar to laying out the footings. The outside surface for the foundation wall is laid out using your construction batter boards that you may have used for your footings or just laying out your general site. And then your forms would be erected for your cast in place concrete walls, or your CMUs are laid to the lines of your batter boards. The foundation plan includes the overall dimensions to interior corners, special instructions, dimensions of special or smaller features, and it's always very customary in any set of views to have the smallest dimensions placed closest to the building with the overall dimensions placed around the outside of the building. So as I go to start constructing everything, I can just kind of read through my dimensions of where this wall is being located out. And because this is not construction based on wood framing or stick framing yet, this is still just using either bricks or concrete, everything is measured to edges, including openings. So if this was stick framing for this opening or wooden, then I would be measuring to the center. But because, I thought for a second my mouse wasn't showing up. Because we have it because it's being made out of concrete, we're measuring to the edges of openings. So all of your drawing sets are going to include at least a wall section showing how the foundation is built, how it's secured to the footings, and any special construction on top of the foundation wall. Although a typical wall section may indicate the thickness of the foundation wall, you should still carefully check around the entire wall of the foundation plan to find any notes indicating varying thicknesses of the foundation wall. So for example, if I needed to support a fireplace above, I may have a thicker foundation wall to help accommodate that. Carefully check that foundation plan to make sure there's any notes. So if we, and I know I've opened up this drawing about 1, 2, 3, 4, 5 times now, but if we check over this plan, we can see that this part of our foundation wall is actually just 6 inches thick compared to the 10 inches thick that we have in all of these other areas. And in this area, there's 6-inch concrete block placed on top of the wall. And same thing in here, we have 6-inch concrete block placed on top of the wall. So it's important to check every area to make sure that there aren't any spaces that have differences compared to some of the other parts of it. Actually, before we move on to the next one, I just want to kind of look at this section for a second. So we have our footing located at the very bottom of our section, and then we can see that there is a dowel connecting it, so a piece of rebar is connecting that to the foundation wall. And then as the foundation wall travels up, sitting on top of it then is our sill plate, which is being held in place with an anchor bolt. Anchor bolts are not shown in a plan view, and I'm pretty sure I have this on a slide in a few minutes, so maybe I shouldn't say it now, but anchor bolts we typically don't see in our plan views, but we can see how they're spaced when we're looking at it in our section view. So we can see here that our anchor bolts are 3/8 of an inch in diameter, they're 12 inches long, and they exist every 6 feet along that foundation wall to help tie that sill plate onto the foundation. Yep, and I knew it. It was on the next slide, so maybe I should have just moved on. So with masonry construction for foundations or CMUs, details may call for horizontal reinforcements at every about second or third course in that wall. It's usually made out of like a prefabricated wire reinforcement that's embedded into the mortar joints. And you can buy those in varying sizes for different sizes of concrete blocks. The height of the foundation wall is dimensioned within your building elevations. So you can't see it in your plan view, just like in your floor plan, you can't see heights of walls. Same thing with your foundation, you wouldn't be able to see those heights. And these are the same dimensions as the ones you use to determine the depth of the footings. So just as the footing was stepped to accommodate a sloping building site, the top of the foundation wall may be stepped to accommodate varying floor levels in what's known as the superstructure, or just the construction that's above the foundation. Your foundation wall can also be built with smaller concrete forms to help form like a ledge, which later brickwork can be built upon. And it can also be kind of a common practice to use 4-inch solid block at the top of the course for a CMU wall. In concrete foundations, anchor bolts are placed at the top of the foundation wall, like I said, which are left kind of protruding out of the foundation so that that wood superstructure can be fastened into place later. And as I said, they're not normally shown on the foundation plan, but we can see them in sections for their spacing. If we're doing a CMU foundation wall, anchor bolts can be placed in those hollow cores of the concrete blocks, and then they're held in place with filling the core with just mortar grout. And grout is just Portland cement, and it has real high strength for it. Other features you may see to attach your foundations, so like in areas where there is a threat of extremely high winds or earthquakes, additional hold down straps, which is what's in this picture here, can be called for, and they're normally only used with concrete foundations. A lot of foundations include steel or wooden beams, which can act as girders to support the floor framing over long spans. And when a girder is steel in your foundation plan, it's shown as a single line with a note specifying the size of the structural steel. If your girder is wood, then it's indicated by usually 2 or more lines and a note specifying the number of how many pieces of wood are and their size used to build up that girder. And so let's see if here on our plan, we have our haunch here. I want to see if there's any girders. I never checked before. footing. Okay, so I'm not seeing on here any girders, so no. Let me just double check. Yeah. So no, not on that plan. But anyhow, now if there are windows are included in the foundation or any openings, then the form carpenter or the mason has to provide those openings to the proper size. So the locations of those windows are dimensioned on the foundation plan, and the size of the windows may be given in a note or in a window schedule. It's important to get the masonry opening to the size of the window manufactured before forming the opening in the foundation wall. The opening has to accommodate the window, and it has to be the nominal size. And so that's why in our foundation plans we measure them from edge to edge. And typically we'll also have a piece of steel L header above any of those openings just to help support any structural integrity that may have gotten lost by creating that opening. The foundation may also include pilasters for extra support, which, as I mentioned before, is just that thickened section of the foundation that helps resist pressure by exerting the earth on the outside. And the locations of all of those can be found on the foundation plan. So in our drawing here, we have several pilasters included just to kind of help provide a little extra strength throughout the foundation. Another special feature you may find is something referred to as a beam pocket. And so that's if you have a girder running across for support and it's to be flush with the top of the foundation, you have to provide a pocket in that foundation wall, which we know as a beam pocket. And they're shown on the details and sections of the construction drawings, and the location of these pockets are dimensioned to on the foundation plans. Now, another thing very important within our foundation construction is to account for drainage. So after your foundation walls are erected and before the excavation of that outside of the wall is filled back in with dirt up until the finished grade line, footing drains have to get installed. And so footing drains are usually perforated plastic pipes placed around the footing in a bed of crushed stone or gravel. If the site has a natural slope to it, the footing drain can be run around the foundation wall to the lowest point and then away from the building to drain by gravity. In areas where there is no natural slope, the drain is to run to a dry well or to a municipal storm drain. At one time, clay drain tile was the most common type of pipe for this purpose. However, now we typically, and I don't know if, yes, I do have it on this one. However, now we mostly use perforated plastic pipe. And so you'll either can find it manufactured in 10-foot lengths of like rigid pipe or in really big rolls of like 250-foot flexible pipe. But when we have our footing drain included in a drawing, we show it in the section view detail. And so that's what's occurring right over here. And in our practice from this section view lecture, we had that pipe running in here with our gravel surrounding it. So that way water can just infiltrate into the pipe and then disperse outside. Okay, I guess I didn't put it on a slide, or maybe I did. No, here it is right here. I was going to say I didn't put it on a slide. So if a floor drain is to be included in like a concrete slab floor, they're indicated in a symbol on whatever floor plan would be appropriate for. So sometimes it's in the foundation plan. Sometimes it's in like the first floor plan. So if you're using that slab if you're using your slab to act as your floor in your first floor plan, then you would put the floor drain on there. So you'd have your symbol for your floor drain as well as then the slope. So the floor itself wouldn't actually be completely flat. It would slope towards that drain to accommodate for it. So another technique that is often used to help prevent groundwater from seeping into the foundation is coating the foundation wall with an asphalt foundation coating. So at this point, subsurface work is outside the foundation wall has already been completed, but you haven't done any backfilling. You haven't started to then put the dirt back in for the finished grade. And you shouldn't do it until the superstructure, the wood structure above the foundation, has been framed as well. So the weight and the rigidity of the floor on the foundation wall help the wall to resist the pressure of the backfill. If you do have to backfill before framing, then the foundation wall should be braced. To help kind of slow the flow of moisture from the earth through the concrete slab, hold on, I lost my train of thought. All right. So sorry. So to help stop water then from the ground seeping into our foundation wall or from underneath in our concrete slab, we can use a layer of gravel over the area before we place our concrete. And so that way I don't have earth directly touching this concrete slab. There's just crushed stone or gravel underneath it. And then we have a plastic barrier known as a vapor barrier that's laid over that gravel to just kind of stop it from getting in there. The thickness of that gravel is measured in mils, and 1 mil is 1,000th of an inch. So they're pretty small. For a lot of vapor barriers, we use probably around like 6 mil polyethylene. Now, in cold climates, it's also a good idea to provide insulation around your foundation wall and a concrete slab. So again, while I have a slab on grade, or while I have a slab foundation or a slab floor, there's also a layer of rigid insulation underneath it. This insulation is just kind of a plastic foam board, that blue board. We've probably all seen it before. And it's placed against the foundation wall and or up to kind of where that haunch would be for your slab footing. And it typically only has to go in about 2 feet from that foundation wall. The heat of the building itself can help keep the frost from penetrating more than 2 feet into the perimeter of the floor slab. Now, like all materials, concrete and masonry work expand and contract slightly with changes in temperature. So our construction teacher at the high school here, he always says that you can count on concrete to do 2 things. It'll dry and it'll crack. And ultimately, it's a pretty good way of living. Pretty straightforward idea. And so your concrete floor, no matter how perfectly it's laid, no matter how many dehumidifiers you have running in there, it's going to expand and contract slightly with those changes in temperature. To allow for that slight expansion and contraction, the joints between concrete slab and foundation should include a compressible expression joint material. And so you'll see that a lot in like big warehouses. So like I'm thinking of if I was walking around a Costco, and you can look at the floor and you can kind of see where there's that little piece of expandable joint, where that way as it expands and contracts, it's not going to crack. This joint filler is as wide as the slab is thick, and it's simply placed against the foundation wall before the concrete is placed. Now, when a house has a basement, the floor of it is concrete slab on grade. And the areas to be covered with concrete are indicated in the foundation plan or basement floor plan. And it's usually done by area, not giving the thickness of the concrete slab and any reinforcing steel to be used. To help the concrete resist minor stresses, it's usually reinforced with a welded wire mesh. Welded wire mesh is sometimes abbreviated as WWM in drawings, or WWF for a welded wire fabric. The specifications for that can all be found in building codes. And where your slab must be supported, or where your slab is rather supporting bearing walls or masonry partitions, it has to be haunched. So when floor drains are included in a slab foundation, sorry, I keep losing my words. I need to make myself another coffee. So where your floor drains are included is where you have to have water to allow to run off. And so in those instances, your slab is pitched, or it's sloped really slightly. And there'll be a note in the drawings that expresses the amount of the pitch. 1/4 inch per foot is pretty common. And so it's the same as like the pitch of our roof, where then, so in our major drawing project, our roof is pitched 3/12. So for every 3 feet we go up, we go 12 feet over. This is the same thing. So in this example up here, it's for every 1 foot over, we go 1/8 of an inch down. 1 foot over, 1/8 of an inch down. So it is such a kind of small slope that it's not really going to be recognizable, but it's still going to help drain that water out. When there might be any confusion also about which way your slab is pitched, there'll be an arrow drawn to show the direction and the way the water is running. So in this example, the water is running there, so that way it goes out those overhead doors. And one moment, I'm going to pause because I had to sneeze and I didn't want to do it over the microphone again. Okay. Last kind of note about slab foundations is that they may also require electrical raceways to be installed in the foundation, or rather just below it in the crushed gravel fill. They must be made so that they don't reduce the structural integrity of the concrete slab, and you have to then kind of keep in mind how large of a size of electrical raceway are you installing in there. So an oversized raceway in that concrete slab may cause it to crack and settle unevenly. So you need an electrician to be kind of there during concrete placement to help make sure that there is no damage happening to any of the electrical raceways. All underground utility systems too, which, do I have that on the next slide or not? Kind of, but no, that's talking about something different. But we can keep it there. So all underground utility systems must be coordinated also prior to installing your concrete slab, especially in commercial and industrial buildings. You may have a service entrance that needs to go into the electrical, into either sub-distribution sections or electrical panels. You may have electrical feeders coming in through different sections, and it requires detailed coordination between that electrician and the contractor, as well as the designer. Other utilities too may have priority over those electrical work. So it may be that if I have a slab on a slab foundation, I still need to run my plumbing through it, or my fire sprinklers, or heating, or air conditioning. So it has to all be coordinated and thought through beforehand. That is, so for me, with my house, not that I would have to pay for any of the damage for it, but that's, for me, is kind of the scary part with my house having that slab foundation, is that all of my plumbing and piping is underneath that slab. And so if there was to be something that happened, the floor would have to be, like, they'd have to come in with a jackhammer and take the floor up to do any work on that plumbing. And a lot of times too, in scenarios like that, you don't know that there's a leak or an issue happening until it's too late, because since it's happening underneath a slab of concrete, you don't know about it until it makes itself known, and by then it's caused a lot of damage to about 6 inches of concrete, and it could be making things worse. But it's kind of just something to consider, and if it's also, is it worth the end result? So for me, to have floors then that help kind of help release the heat, and also are super easy to clean, for me it's kind of a worth it win-win. And especially since I don't own the place, if something were to happen, I wouldn't have to pay for the plumbing to get fixed. So to me, it's kind of sweet. Maybe my landlord wouldn't think it would be great for the plumbing to explode. So speaking of plumbing, let's talk about some sewers. So your building sewer carries the waste away from your house to either a municipal sewer system or to a septic system. And this is more than just also the waste coming from, like, your toilet. It's also your shower drain and all of your sink drains, your washing machine. All of that is all getting kind of drained towards that same area. You could install like gray water systems to help take things from like the sink, and depending, I guess you could do the washer too. Most people would consider a shower black water. So black water would mean that it would have like bacteria and like feces in it. And a lot of people consider showers to also be black water, just because if you're washing yourself, and hopefully if you're washing yourself well, we are in a pandemic, so please take a shower, that there might be then some human bacteria or matter that you wouldn't necessarily want in a gray water system, because gray water systems then can be used to like water your land, or just for, they can, a lot of times we'll see gray water be pumped back into a toilet for then to be flushed and turned into black water. There's a system at, I don't know if they actually installed it or not, because it was like in design works while I was a graduate student, and it was still, I think, being in design after I graduated. But at Haircut 101, they were working with the department to design a gray water system that took the water from the sinks from when they like washed everyone's hair and then used it in the toilets. And so it was just to try to kind of help clarify that water, get maybe some of the icky stuff out, just because like hair bleach and everything sitting in the toilet, and then that water can be reused and reduce just clean water usage a little bit. But anywho, I'm getting off topic. Sorry. So because our sewer lines usually rely on gravity flow, they are larger in diameter, so they're usually about 4 inches minimum, and they are pitched or they slope downward to help provide flow. Now, because water supply lines are pressurized, and so are gas lines too, the pitch of those are really not important in the insulation, and that's why the sewer is installed first, and then the other piping is routed around it as necessary. So my water supply line for my sink, it's going to be pressurized to get it there, so I don't really have to worry about it. But with my sewer line, I would like to rely on gravity for it. The pitch of the pipe is usually given in fractions of inch per foot, and a pitch of a quarter inch per foot. That means for every foot we move horizontally, we move a quarter of an inch down. In some cases, in some cases, your sewer may have to flow uphill. You may not have an option for it if the municipal system is uphill from your house, then it has to go uphill. And so in that example of the lake house that we were looking at a couple of times, which let's look at it one more time. If we look at the site plan here, the septic system and everything is sitting at an elevation of around 348 feet. The building itself, or where it's coming out of, is at 342 feet. So it has to kind of run uphill to get here. And also the municipal water system is all the way here on the street. So we kind of our hands are tied a little bit. And that's when you would use a grinder pump to just kind of help push the sewage or drainage uphill. And the grinder pump just grinds solids into these small enough particles to be pumped into sewage with fairly low pressure. So any plumbing that is to be concealed by concrete work must be installed without fixtures, or it must be roughed in before the concrete is placed. Because the plumbing contractor installs all the plumbing inside the building line, this phase of construction is something that we'll discuss later in the course when we go over mechanical systems. If we have some time to do that, we may not even touch on mechanical systems or plumbing. It depends on how the course goes. Right now I have it as a possibility. The workers who install the sewer have to be able to determine the elevation which it passes through the foundation and the pitch of the line outside the building. The sewer line may be shown on plans as a solid line or as a broken line, and although it's usually labeled, it's not always. When the sewer isn't labeled, it can still be recognized by its material, its pitch, and its ending place. Now, in most developed areas, the building sewer empties into a municipal sewer line near the street. The contractor for the building is responsible for everything from the municipal sewer to the house. In less developed areas or kind of more rural areas, but it's even the case in some suburban areas, the sewer carries the sewage into a septic system. The most common type of septic system includes a septic tank and a drain field. So the septic tank holds the solid waste while it is decomposed by bacterial action. Then a liquid passes through the baffles and it flows out of the tank into a distribution box. And then the distribution box diverts the liquid into leach lines. And these are just perforated plastic or loose-fitting tile lines, allowing the liquid to be absorbed by the surrounding soil. The liquid gradually evaporates from the drain through the soil into the drain field, which it's usually made up of a layer of crushed stone, and then there's dirt on top of the entire scenario. The design of your septic tank is closely regulated by most health and plumbing codes. You need to check these codes before designing or installing any septic system, because otherwise you're going to have a bunch of gross doo-doo sitting in your lawn, which no one wants generally. So building codes will often require a percolation, almost couldn't say it for a minute, test before the system can get approved. So in a percolation test, holes are dug and then measured the amount of water poured into each hole, and it's the amount of time required for the water to drain into the soil indicates how well the soil will accept water from the septic system, and this ability to accept it is called percolation. And the location of key elements in the system are often shown in the plan. So you will see, and we can go back again to this site and foundation that I have open in several places. So we can see here that this is using a septic tank, and then here is our 1,000 gallon concrete septic tank, here's our distribution box, and then this is our drain field, which is a tile drain field, and it was approved by the city health department. Sorry, I just sneezed again. I'm getting better at pausing about it though. And so, like, this would not be a good place to, necessarily build anything. Or maybe actually would be a pretty decent place to make a nice garden on top of it. But that's where this septic tank is draining in this drawing. Okay. Another thing to think about is that there are lots of different materials that are used to make all of these different pipes and fittings. Traditionally, we used, or like back in the day, we used cast iron and for sewer pipes, and then supply pipes were made out of galvanized iron or made out of steel. Then as PVC became available, it became the most common material for drainage and waste and vent piping for sewers, purely because it requires less energy to manufacture than cast iron, and it lasts almost indefinitely, and it requires a lot less time to install. The downside, though, is PVC can't withstand heat very well, so it can't be used for hot water. Same thing too with different materials. So like copper with soldered fittings has been used a lot for supply piping because it's non-corrosive, it lasts longer than iron and steel. Issues that we have very commonly in Watauga is that a lot of people use well water here. I have well water, and it's sometimes slightly acidic, and the acid does corrode copper pipes. It's not really a concern if you're using a municipal system, because the water is treated before it's pumped to you to help control that acidity. So in kind of recent years, copper has become more expensive, and there now is kind of two types of plastic pipe that have been developed to use where copper was the standard. So C PVC, which is chlorinated PVC, which is chlorinated polyvinyl chloride, which is a mouthful because it's just chlora, is pretty inexpensive. It's non-corrosive. It's easy to install. And then PEX pipe, which is cross-linked polyethylene, is more flexible, so it requires less fittings. It's quick to install. And so those two types are used a lot now in construction today. One of the kind of, I guess, green issues to that is that manufacturing of all plastics requires those petrochemicals. But, you know, as the percentage of total materials in a home and the amount of piping material is small, plastic pipe isn't really considered to be like that big environmental killer. And in the long run, it still is more beneficial than using copper, which would then have that ability to corrode and also is kind of a more finite resource. Well, I guess not a finite resource because petroleum is more finite. Really, I guess the point of this little rant here is that there's really no one best material for piping in green home construction. There's the pros and cons to all of them. Okay, kind of wrapping it up then for today. Last thing to consider is your electrical service, which is the wiring that brings electricity to a house. And there's two types of electrical services. You have overhead or you have underground, which was just lines that are buried in the ground. Overhead services involve a cable from the utility company to a transformer or a pole to a weather-tight fixture called the service head or the mast head of the house. So this service head is mounted on top of a pipe, which serves as a conduit for the meter receptacle. And in underground service, the cable is buried underground. Ooh, it sounds just like it works. Although electrical service is a site utility, it's not usually installed until the building is fully enclosed and the envelope is sealed. The electrical service to residential and small commercial buildings is pretty similar. They both can use either option. So the thing with electrical services is that it only has one distribution point, which is that main electrical panel. In heavy and commercial and industrial ones, you'll have multi-conductor feeders, and you typically have them as underground services. You may have to kind of coordinate for some of those larger structures with additional utilities. But we're not really going to focus, like I said, on a lot of that industrial, commercial construction in this class. We're going to kind of look just at residential. So if we look again at this site plan here, we have our sewage line then in our site plan. And let's see then where our electrical feed-in is going. So I saw we have our inverter here. Now that's just our grinder. Where's our electrical coming in? And that's our water entrance. Let's see, curious, because I'm not seeing it. Okay, well, I'm I suppose, let's see here, if we go to this one. Let's see. Bear with me for a minute, or don't. It's okay if you don't. Let's see if we can find it in the floor plan for lower level. Looking for the panel box. Which should be, if it wasn't in this utility room. Not sure. I'll have to look at the plans a little bit more, but I'm not going to keep you guys here forever and ever and ever while I go over all of these plans. So here then is a site plan with all of the utilities. So we have our, oops, of course that thing pops up as I move my mouse near it. So labeled with that G is the gas line entering the building. And then we have our municipal water entering right here. We have our buried electrical service coming in. And then we have our septic tank coming out to our distribution box and our leach field. So, and we even have here that the pipe is 4 inches in diameter, PVC pipe with a pitch of 1/4 inch per foot. So that means it's just slowly going down to get into that septic tank there. And that is okay. I finished way before time, but that's cool with me. That is a I guess brief-ish introduction to foundations and footings. And we'll play around with drawing them some more in your big hand drawing project, and when we get into SketchUp, and when we get into CAD, and even more. So please make sure that you submit your guided notes on As You Learn. If you have any questions, please email me. And thank you for watching. Have a wonderful rest of your day or night or weekend or whatever it is you have going on.